Alright, AP, in the next video we have our favorite equation, products minus reactants. But we're just going to do it with entropy now. So learning target here, nice and simple. Calculate the entropy change of a physical or chemical process based on the absolute entropies of the species involved in the process. Now what they mean by this absolute, just like if you were in math class, if you had a value right here, when you take an absolute number, that just means that the number is going to be positive. Okay, and I want you to see something with the appendix. Okay, look at all these S values. Not one negative value for the S's. See? All positive. So what they mean by absolute is every single one of these S values are all positive. Okay, so the entropy change can be calculated from the absolute entropies of the species in that process. So products minus reactants. There's a big change compared to delta 8 when we did products minus reactants. Sorry, I got the hiccups. So be very careful of the moles, okay, when you are doing this. So if you do have moles in the equation, you do have to still multiply by however many moles that you have, okay? So products minus reactants. With the units for delta S, as you see in the appendix right here, the delta S has J over moles times K, okay? So right here, the typical units when you do products minus reactants is J over K. When we use this equation, oops, not H. When we use the equation in 19.2, we said it was a Q reverse over temperature, and that was J over K. But when we do products over the reactants, we tend to still keep the moles in there, just like when we did delta H. Delta H was kilojoules per mole. Okay, so with products minus reactants, it's still J over K, but we keep the moles in there because it's a reaction. So the absolute entropy can be determined from very complicated measurements, and we don't need to know how it was calculated from that scientist back in the day. The values are based off of that third law of thermodynamics. So what they did was at absolute temperature, that's 0 Kelvin for a perfectly pure crystal solid, that entropy was 0. So they based all of these values that you see on this chart, they based it off of the third law of thermodynamics. Okay. Molar entropy obviously has moles in it. Okay, so the word standard, that little degree sign, standard state, which is 25 degrees Celsius, 1 atm, never going to change. Molar, because we got to throw the moles into the units. Okay, so usually, as we said, delta S is J over K, but now it's going to be J over moles times K. And we already talked about what delta H would have been. Some good observations to make before we just start plugging and chugging. It's a very simple equation. We can't mess this up, okay, unless you are that person that went reactants minus products. Standard molar enthalpies, this is the big one. Remember in chapter in delta H's, okay, if they were elemental form like oxygen or sodium, or just looking at like titanium, chlorine as a gas, every single one of those delta H values, they would have been 0. I don't have to look them up. Well, you do now. Okay, there is no such thing as a standard elemental value for entropy because every particle moves, so they all have a value. Even solids sitting there vibrating, they even have a value. So see right here, if it would have been like, look at cesium, for delta H, it's 0 because that's its elemental form. Well, as a solid, it still has some movement. Okay, so even like a gas, like chlorine, as a gas diatomic, that H value is 0. However, he's a gas. He's got a lot of movement. Okay, so ladies and gentlemen, you got to look up every value. Okay, and I'm sorry, I didn't write the rules. So for this one, look up all S values on that appendix. Okay, and we're all kind of crying inside there. It's not rocket science, ladies and gentlemen. We've been talking about movement, so the values of gases are definitely greater for a gas than liquids and solids. But remember, they're still all positive values, regardless. The S, entropy disorder, it does increase, usually with molar mass. Okay, so basically the heavier the molecule, you would think would have less movement. It's slower, but according to the rules, a molecule with a greater molar mass has a greater entropy. Let's kind of look at that. I really never looked at it through the molar mass side. I've only ever looked at it through the entropy side, but kind of look at these two. You got 2 carbons versus 3 carbons, 6 hydrogens versus 8. They're both gases. And as you see right there, there is a difference. Okay, so even if you have one and then right here C4H10, even greater molar mass. Okay, so molar mass trumps it. We already know that the more moles you have, the more disorder. Okay, so when you have somebody like C2H6 as a gas versus C4H10 as a gas, you're talking about somebody that's about 300 JK mole, and I better look up that value before Lily says I had some crazy dyslexia. Yep, 310. Haha, Lily. And then right here, that entropy value was around 226 JK per mole. So definitely the greater the molar mass, the more movement. The more moles, more movement. Okay, so right here for that letter N, just be very careful. You have to make sure you still multiply by the moles. Okay, so let's try 2 of them. And I added these in, ladies and gentlemen. Okay, so refresher, Miranda, I'm giving you a shout out. Make sure you remember isothermal processes. So in the equation, ladies and gentlemen, because you're going to see this coming up in another video, when you're doing that delta S, and when you're seeing Q reverse over temperature, this delta S, and I don't think I put it in the actual formula, but I have it here, it's the surroundings. Okay, so you're finding out, you're calculating the entropy, the disorder, the movement for the surroundings here, not the system. But we also can look at it like this. Remember that Q right there at constant pressure could also be delta H over that constant temperature, but this delta H right here would be the system. So how is the system losing or gaining heat? And you actually do have a negative here. Okay, and this Q right here could also, as you see right here, could be Q of the system. Okay, so remember it has to be for a reversible process, and the disorder of the surroundings is gaining, is increasing as the heat of the system is losing. So let's make sure we're getting that. Okay, so as the system loses heat, okay, so that Q is negative, your entropy is increasing, okay, because of the surroundings. Someone's got to gain it, okay? So you're losing heat. Obviously, that heat must be going to the surroundings. So if we had our box right here, our system, that heat is coming out. And what's happening to the surroundings where that heat is coming out? Well, the surroundings are gaining that heat. And because the surroundings are gaining that heat, you are creating more movement. Because what did you probably change? Well, you probably changed some kinetic energy. And I know, ladies and gentlemen, it says isothermal. That means constant temperature. But you can still make somebody have more energy than the other by changing some heat. Okay, put that Bunsen burner up there. So that is what's happening. I just wanted to make sure with that equation right there. And definitely, I would add that to my equation sheet. So that way we keep track of what equations we need to know. Okay, and we already know that Q equals that delta H and that constant pressure. So I have 2 examples right here. Okay, and you can add it to a piece of paper to the notes. Calculate the change of standard enthalpy, so I want that delta S, of the system for the synthesis of ammonia. Synthesis, just a fancy way of saying combination, because you know Rodriguez is not that nice to give you a balanced equation like she did on part 2. So if I want the synthesis combination reaction of ammonia, and I'm just going to say ammonia as a gas, from their elemental form. Now it doesn't matter that their elemental form is on this equation, ladies and gentlemen. We still have to look up all the S values. So for the N2 and H2, we do have to balance those equations. And I strongly suggest when you're doing products minus reactants, kind of have some whole numbers. It does help. So 2 there, a 3 there. And now we're going to list the delta S values. Now, be careful that temperature. That temperature has to be that room temperature, 298. Okay? So I'm going to have my screen over here as you're looking through all my personal information. There you go. Let's make him kind of go over here some. There we go. All right, all right. Okay, so we have N2, so we need to find some nitrogen, and N2 as a gas right there. Remember this last column right here is the entropies. So that is 191.5. So Lily, make sure you're watching my numbers. Joules mole K. And for hydrogen, hydrogen's back up here, I believe. Where'd hydrogen go? Oh, there he is, right there. H2, you have 130. So even right there, ladies and gentlemen, look at the difference between H2 and N2. Obviously, N2 is definitely more massive in weight than that H2. And even though they're gases, that nitrogen's still going to dominate that reaction. Now, we are going to have to multiply this by 3. And then I got to go back and look at ammonia right over here. Ammonia as a gas is 192.5. So 2 times that 192.5. Remember, it's J mole K. Okay? So always have to write APR equation. Don't forget that little degree sign. We put reaction, and we show them that we're going to add up all of the standard entropies of the products, and we're going to add up all the standard entropies of the reactants. Okay, so let's get our trusty calculator. You know you better check Rodriguez's math. So right here for my products, I do have, and I'm just going to put in parentheses, so I got that 2 times 192.5, and we got some 385 J mole K, minus, because I like to use parentheses around this stuff, I need to add these reactants up. But first you got to multiply that hydrogen. So 3 times 130.58. And I'm going to add that to the 191.5. So this together, 583. So do you see these values, ladies and gentlemen, how everything is positive? Okay, because they did say the absolute entropy values are positive. But in the end, your answers can be negative because you're going products minus reactants, which means one part of the equation can have more entropy than the other. And this is kind of how you check your work. You see this right here, these things called gases? In the previous video, I told you if you create more disorder, your entropy will be positive. Well, look at what we have here. For our reactant side, we have 4 moles of gases. But our product side, we only have 2 moles. Did I create disorder in this reaction from reactants to products? No, I actually made order. I actually have less disorder. Okay, so if I have less movement, less entropy, that means this answer should definitely be decreasing and possibly negative. Okay, so you're going to see questions in the book. We're going to do them for homework. They're going to say predict the sign. So if I was going to predict this delta S sign, I'm saying it's probably going to be negative because I created less movement. So remember in the video I told you pay attention to gases, then pay attention to the moles of gases. Who has more gas movement on which side? So if I'm looking at these numbers, I know this answer will be negative. So I'm making just a little side note here. The entropy individual values, all positive, okay? However, the calculation for the reaction, products minus reactants, it could be anything, minus, positive, whatever, okay? And this definitely looks like a negative number. So 385, and before someone gets after my sig figs, this was 385.0, and then these two had 2 after the decimal. All right, I'm just trying to save my points here. 583, because I love how you guys come after my work. Trying to get those bonus points. 198.24, and we still have J mole K. So remember, ladies and gentlemen, not kilojoules here, not kilojoules. Okay, so that delta S reaction, definitely I have created less disorder. And you could even say it in a different way. You could say I actually created more order. Okay, you could even have either one. This one right here, number 2, ladies and gentlemen, I would like you guys to try number 2. Just be very careful. You do have a solid, so let's make sure we have our values. I just want to double check. Yep, aluminum's up there. Hydrogen, aluminum as a solid, water as a gas. Yep, you could do this one. Okay, show that work, ladies and gentlemen. See,